Um, Hello, everyone. Thank you for attending our talk. Today, we're going to talk about testing and benchmarking on hardware of hypervisors and operating systems. My name is Sebastian. I am a software engineer at Cyberus, and next to me is Markus. So,
yeah, I'm tech lead at Cyberus Technology. Yeah.
Okay. So let's start. Yeah. Okay, so who are we? Cyberus is a small company from in Germany. So we have about 25 employees all over Germany, and our headquarters is in Dresden in Saxony. And so we have a strong focus on virtualization. For example, we build a KVM backend for VirtualBox. There is a talk tomorrow at, I think, 3:45 p.m. about that by our coworkers Julian and Martin. So I think you should attend that. And we also built a microkernel-based hypervisor in our early days. And for that hypervisor, we wanted testing on all supported hardware. So, for example, just different generations of CPUs have different features, and we wanted to test all these features that we support. We later switched to Linux-based virtualization, for example, KVM and VirtualBox. But the infrastructure we built for our own hypervisor proved to be very helpful for testing KVM patches, different Linux kernel configurations, and for benchmarking all of that. So over the years, we gathered a lot of knowledge about test automation. And yeah, so Markus will tell you now about our solution to our testing needs.
Right. So what we built is a service that we internally just call SoTest. And just from a very high level overview, what we do is we have a description for what kind of test do we have, what kind of hardware should the test run on, and we have complete bootable OS images. And we want to put these two together, boot them on real hardware, figure out whether some tests succeed or fail, and get the information back as a single decision point for is this change that we just tested, is it good or is it not good? Yeah, that's basically just a high-level overview. We have a package of some binaries and some configuration files. We hand it over to this SoTest service. This SoTest service orchestrates different kinds of machines depending on which tests which machines the tests are for. We obtain some results that are failures or success, and we accumulate them into a general success or failure. I hope that's not too surprising in the general idea of what you would do when you test stuff. So yeah, we have some kind of web UI. You have individual test runs, and you have individual items in these test runs with a whole matrix of some kind of tests or benchmarks on different kinds of hardware. And what it looks like in the real world is this is a small cutout from our server room where we test different kinds of laptops. You see some laptops in the front here. There are laptops open to 180 degrees in the back, just stacked behind each other. And we have an additional server rack with servers in there, and there are other form factors that we sometimes need to test. And what we want to talk to you about today is the challenges that we encountered and what kind of solutions we found for these challenges. In particular, we want to talk about how we can make arbitrary hardware remote controllable, because not all hardware is designed to be remote controllable. How we can integrate this on hardware testing into the actual development lifecycle. So, for example, how we can integrate it into tests that run for each merge request or for each change. How we enable performance benchmarking, we want to talk about how we can handle throughput issues with this whole thing, because testing on hardware is much, much slower than just testing software and some kind of VM. And also we want to talk about how we may be able to handle some kind of flakiness in the whole system, so we can have somewhat reliable test results. First, let's talk about how we make arbitrary hardware remote controllable. There are basically three things you need to do to control a hardware in some way that it's useful for a test. You need to power cycle the target hardware. You need to configure what kind of software is going to run on it, and you need to obviously observe some kind of behavior of what the test is doing or what the machine is doing. For power cycling, there are some off-the-shelf solutions for management software for servers, but as you may have seen in the picture, we have a lot of laptops, and laptops usually don't have these kind of interfaces. So you need to figure out some way to do it. If you're lucky, you can do it with switchable power sockets that you can switch off remotely. Because some laptops you can actually configure to start when there's a loss of power, if you can somehow circumvent the battery. But also for those, you cannot do everything. And I'm going to show a few pictures here. We have a Raspberry Pi header that we actually use to simulate power button presses by bridging the corresponding contacts either in the front panel connectors that you have in some desktop PCs, or if you have laptops, you sometimes need to solder wires to the power buttons. We didn't have to do that for a long time, because in the later generations of laptops, you usually can go the way of do it with the switchable power sockets. But we have quite a few laptops where we have some kind of hole in the case and some wires coming out of them. The second part is the software configuration. That one looks easy at first because you can just do network booting, PXE booting. In fact, it really worked well as long as we, PXE booting in isolation worked really well as long as we were doing microkernel stuff, because PXE booting works great for small kernels and small payloads that you want to boot. But as soon as you get into the area of booting actual Linux images, then the free memory regions just aren't enough for deploying gigabytes of init-RDs. So we had to figure out some kind of way of loading software after the boot, or if I just have a small initial system that then pulls down a huge squash FS or something. That was a bit difficult, but it's basically a multi-stage step now, where we even at some point pull down like 10 gigabytes of Windows images for some VM tests. And I think at that point, it's obvious that you can't really do that with PXE boot anymore. The last part, the last thing that you need to do is observe behavior, obviously. And here again, we started from a microkernel perspective, where we didn't have a lot of flexibility to implement whole USB stacks or network stacks. So the only thing we really could do that really worked well over a long time was serial. So the old RS-232 serial. And there's a lot of management to do with that as soon as you have a lot of machines, because at some point you can't just plug all of them into the server directly. So we invested in some kind of serial console servers that abstract them away over network. And another thing we had to do, because again, laptops may not have a serial interface that you can just plug in. And one of the I think the one of the most adventurous thing we did was some kind of Thunderbolt to M2 disk to PCI Express to then serial adapter that at the end helped us get all the necessary information out, the logs and the test results. Yeah, right. So another thing is USB to serial converters, but again, we cannot do them on the whole low level. And this is a piece of the architecture that survived from the microkernel architecture now to when we're doing actual tests with Linux and KVM. I'll hand over to Sebastian again for the next part.
Okay, so now we have our nice SoTest controller, and we can send tests to it, and it will schedule it on the right hardware and report the results back. But as most of you, I think, know, is that the best tool won't be used if it is inconvenient to use it. So you can just let the developer do all this assembling of the binaries and the configuration files. But yeah, as I said, I think this won't be used. So the first thing we did was to integrate it into our GitLab CI. So for every merge request and for every commit, the CI will just assemble everything, push it to the SoTest controller, and report the results back. So for every merge request, we would see whether the change still works or not, and only merge requests where all tests are green will be or would be merged. So this increased our confidence that our products actually work. But as a developer, so if you implement a new feature or you add a new test, you don't want to push every time and trigger all tests just to see whether one test works. So you need a way for the developer to conveniently schedule single tests. And we later adopted Nix and NixOS in our company. And with that, it was really easy to build the same test packages on the developer laptop as we built in the CI. And so, and to select single tests and all of that became kinda easy after some work. So now the developer can just implement a feature, select the test, and on which hardware to run the test, and with a few clicks, we can push our tests into SoTest, and this is incredibly helpful. And yeah, so we get our feedback for our features really fast, and this helps a lot when developing new features. So yes. Okay, so the next step is performance benchmarking. So now that we have all of that, we can really do the performance benchmarking because we don't need one coworker that has like 20 laptops and runs the benchmarks and I don't know, writes results in some Excel table or something like that, because we can just push our benchmarks, because benchmarks are just like tests, except that you don't get it works or it doesn't work, but you get a number that indicates the performance. So benchmarks are a lot like tests. There are just a few differences, but yeah. So integrating that was mostly kinda easy. The things you have to consider is consistency. So you want for every one of your benchmark with the same software on the same hardware, you want the same results. And especially on laptops, this is kind of difficult because if your laptop is in lab mode, it won't, also it tries to be a little bit colder, so it's not so hot on your lab. So if you can't control the hardware, so you can't control whether your laptop is in lab mode or not, you won't get consistent results. And the other thing is that operating systems sometimes need some time to settle down after boot. So for example, if you start your benchmark right after you booted your Windows, your results will be all over the place. So this is another thing you have to consider. But if you spend some time and hard work, you can get some nice benchmark results, and you can see at an instant whether your change increases or decreases the performance. And then you can also have some nice pictures that you can show to your manager. So for example, here we wanted to see whether our KVM backend performs, or how our KVM backend performs compared to the VirtualBox kernel driver. And so the baseline here is the VirtualBox kernel driver, and you can see that the KVM backend performs worse for SEAT and better for NVMe. So you can do a lot of nice stuff with that. So it's worth the hassle. Okay, so now you can build nice tests and nice benchmarks, and if you can do that, you will build a lot of tests and a lot of benchmarks, and you will come to a point where the pipeline just takes a lot of time. And then you have to optimize your throughput. And so the first two things are kind of obvious. So you make some tests and some benchmarks optional, and the developer or the reviewer of a merge request then has to decide whether it is necessary to run a benchmark or a test right now, or whether we can skip those and just merge right away. So yeah, this is, I think, kind of obvious. And the second thing is to skip reboots. So if you have multiple tests that don't influence each other, then you can just merge them into a single test. And because reboots, especially on servers, takes a lot of time and can slow down your CI. So these two measures will make your CI a little bit faster. The next thing is what we call any items. So if we have tests where we think we don't have to run it on every hardware platform because it will behave on all hardware the same, we call it an any item. And yeah, so then if you have a lot of any items, they can run in parallel on different hardware platforms. And yeah, I think this also speeds up your pipeline. Yeah, so scheduling or priorities, this just means that the merge request pipeline has a higher priority than your nightly pipeline. So this won't make your pipeline faster, but at least your merge requests aren't blocked by your nightly pipeline, for example. So yeah. And the last thing is caching. So we know that if we don't change our software, if we don't change our code, we will have the same test binaries. And so into our SoTest controller, we added the possibility that the SoTest controller remembers the hashes of a test of all the binaries and the configs and all of that. And if the test controller sees that it already ran some tests, it will just show you the old results and won't rerun the tests. But this only works if you really have the bit-by-bit same binaries and same configurations. So this may not be very easy, but especially with Nix, this is very possible. And then you will have at least a faster pipeline. So yeah, this helped us a lot. Yeah, and the last thing.
Yep. Let's talk about flakiness, because you may have realized there are a lot of moving parts in this. We have a lot of optimizations for throughput. We have the one picture that was like 12 adapters put into each other just to get some serial out of a laptop. There are a lot of moving parts, and sometimes they just fail. There can be network issues, there can be the machines in an unexpected state, it didn't turn off correctly. There could be just hardware issues and you need to replace some part of the 12 adapter chain. And we found it crucial that the test infrastructure itself can figure out whether, for example, the machine that is just running a test does not answer because it is a problem in the infrastructure, in the test infrastructure itself, or if it's an issue of the test itself. It may not always be possible to differentiate between these cases, because the lines between what is test infrastructure and what is actually the software that's being tested are kind of blurred at the point where you load some squashfs after actually booting with Pixie boot. So it's not really always possible to figure out, is this an infrastructure issue or is this a test issue? But I think we found at some point some okayish way by retrying certain tests if we believe it is an infrastructure issue, and we found a certain way. We don't have a perfect answer for that, but that's just a problem that you're going to run into it if you have this many moving parts. Yeah, I mean the issues in the test itself. You want the user to actually realize that there is an issue, and the infrastructure issues, you just want to shield the user from these. But yeah, as there's a lot of work going into actually streamlining the user experience at that point, because again, if the infrastructure just throws many flaky tests, just throws failures, and you're just going to hit retry every time, then users are going to lose trust in the infrastructure, and it just doesn't matter anymore, and everything's going to be skipped anyways. Yeah, so sadly not a great solution here, but at least some very mindful thoughts. As a summary, it's a very short summary, but we know that automated testing on hardware can be really hard. But what we found is that it actually pays off. The whole automation around it, being able to just send off a benchmark for some kind of change that you just did, and figure out within, at best, minutes, maybe hours, whether performance changed significantly. You can be able to figure out within a merge request whether there's any significant change. That's actually very useful, especially when going into kernel drivers and when doing very low-level programming. So yeah, that's basically our takeaway from all this. It really pays off to actually invest in this. And I think we don't know quite exactly yet how all this infrastructure fits into all the KVM effort that we are now doing. But yeah, we are still figuring it out. Yeah, I think that's it. So we can start a discussion of 5 minutes till the next talk.
Couple of questions. So first of all, if you want maybe to have a later discussion about how you can integrate it into KVM QEMU, we have a test framework called HCKCI that uses QEMU KVM for testing for virtualized devices and drivers. So let's talk how we can work together. But I have several questions. So one, do you use Ironic for hardware provisioning? Because then you can use kind of VM images to provide your hardware, and it's part of the OpenStack Foundation's really nice project that you could use.
Yeah, I know of the project, but no, we don't use it. Many parts of this are actually very manually built for better or worse reasons, manually built by us. But yeah, no, we do not use Ironic. It's really just a plain network boot into a few additional downloads.
The other thing, you said you have some problems within those installation drivers. Take a look at HCKCI, because we have kind of a lot of code there, including certification installation before, so the Windows drivers installation will be very smooth. And the third thing, gathering crash dumps from the hardware. What do you have some tips? What do you do?
I think I didn't understand.
Crash dumps. So if OS crashes and you have some crash information, how do you handle it?
For Linux, we basically have a whole extra channel where we get the whole kernel log, and we get additional information that is then put into the kernel log. So the logic is basically if something crashes, we have some kind, and we figure out, oh, there's a kernel panic in there. Then there's some time where we still gather additional log, and then we just shut off the test so it does not clock everything because it's still stuck. So basically we try to gather as much information as possible, and then we just shut the test down and go on with the next test or with the retry if the heuristic says, oh, that was maybe an infrastructure issue.
Thanks.
Just a quick question. So how do you recover from the previous test failures? Like, for example, if the system crashed, right? You have to last known good state and recover from that?
Yeah, so the last known good state is usually recreated by powering off the machine completely, the target machine, and then starting it again from a network boot state. You may not always be able to have a completely clean state. For example, if there was something written to the disk, or if there's some kind of other change. But that's basically the only thing we can do. We can just try to cut power, get the machine into its original state, and then just start the next test.
You talked quickly about batching up tests to save time, and I was wondering whether you had a good way of figuring out whether two tests actually interfere with each other in some way, and also whether you maybe got it wrong at some point and that caused maybe, for example, some test flakiness later on and things like that, whether you have some stories to share there.
Yeah, so I think the one thing where we encountered flakiness was in our infrastructure. If you have 10 machines that are downloading Windows images at the same time, then yeah, sometimes the downloads fail because I think at that point we had a 1G connection between the server where the images were and the test machines. Yeah, so there are some issues there. I think for this specific issue, we try to counter it by using torrents. So the machines just torrent some images, and if it's the same image, they just pull it from the source. That sped up everything and also fixed some kind of flakiness issues and introduced other flakiness issues because torrents are sometimes weird. Yeah, so the whole batching is the machines are largely independent from each other, except they use the same infrastructure to get the tests. So we also only have single machine tests right now, so you can just do one test on one machine. So the interference between the machines is pretty small, I think.
I was wondering also about if you have two tests, how you decide that you can batch these two tests without, for example, rebooting or something.
Oh, got it. Yeah. A trial and error.
Okay, I see. Right. Thanks.
So what drives your decisions about what hardware you're going to test on? I mean, I assume there's a reason why you've put yourself through all this pain to do all these tests on laptops, right?
Yeah. So the decision, so which hardware we test on is largely decided by who pays us for giving them software. So yeah, basically it's a customer requirement. Okay, we need your software to run on this kind of hardware, and then we need to figure out how we do it. I think we don't always have 100% coverage on all the hardware we need to do, but we try to basically do a sweep over all the different architecture generations and everything. So yeah, it's a trade-off there as well.
Thank you. We are out of time.